In a ground-penetrating radar, the radar pulse is directed towards the ground. When the pulse first hits the ground, some will be reflected and some will go into the ground. As the pulse travels through the ground, it will also be absorbed by it. Eventually, the energy of the pulse will diminish to zero. But until such time, materials in the ground that are along the path of the pulse may reflect some of the energy of the pulse back to the surface. These reflections happen on the surface of these buried materials, or, as is often stated, these reflections happen at the interface between different materials. The same thing happens when we shine a light in a container filled with oil and water. Notice the reflection on the surface of the oil, at the interface between oil and water, and finally, the reflection at the bottom of the container. If we had a really accurate clock, we would detect that the reflection from the surface of the oil happens first, followed by the reflection from the oil-water interface, and finally, the reflection from the bottom, which really is a glass-air interface. Since the same effect happens to our radar pulse, since radar and light are both electromagnetic waves, the intensity of these reflections from the interfaces, however, will be vastly different for radar and visible light. The delay in receiving the multiple reflections will tell us that there are multiple materials below the ground that we are scanning. It will also give us their distances. If we analyze the intensity of each reflection, we can estimate how much energy was absorbed in each layer. While not unique for every material, it will help us narrow down the type of material in each layer. Analyzing additional parameters such as Doppler shift, frequency response, and wave diffraction further narrows the possible material that's in each layer. They also help achieve better imaging resolution.